Today we're going to start on the worksheet called Exponents and Logarithms. Okay? Before we actually start on this worksheet, I want to be clear with you about this section. Okay? Usually when we get to logarithms, people freak out. Why? Because they've never done it before, so it must be hard. Okay? So I want to approach it from a different angle, get you thinking a different way about it, and hopefully that will make it a little better. Okay? So think with me for just a moment. What do you know about the Justice League? What do you know about the Justice League? Who's a member of the Justice League? Superman, Batman? I don't think the Hulk is.
Those are all Marvel characters.
Superman, Batman, Martian Manhunter.
Spider-Man's Marvel.
We have 3 so far. We have Superman, Batman, and Martian Manhunter. Okay, time out. Let me do this instead. Okay? The following are members of the Justice League. Superman, Batman, Martian Manhunter. No. Help me out. Wonder Woman, Green Lantern, Hawkman, all sorts of people like that, right? Not any Marvel comics. We're talking about DC, right? Right? Talking about Justice League. Okay? So, like, what do? What's their job? Superhero stuff, right? They help people. They fight for justice. That's why they're called the Justice League, right? Okay? They're all quote-unquote good guys. Yes? Okay? So, do any of those people that I named for you, with Shad's help, did any of those people that we named for you, like, do they have exactly the same superpowers? No, if 2 people had the same superpower, one person would be irrelevant, right? So, I mean, yeah, it would be nice if we had 2 people that could both fly and both shoot laser scissors out of his eyes, and except they would both be dangerous to, like, kryptonite. That would be dangerous to them, right? Things like that. We don't want that. So let's talk specifically for just a moment about Superman and Batman. Okay? We're comparing and contrasting Superman and Batman. So that's an English skill, isn't it? Didn't you have to do that in the English classes? Okay. Comparing and contrasting Superman and Batman. Alright, so Superman can fly and Batman can't. Right? Okay. Superman can shoot laser beams out of his eyes. Batman can't. Batman can... He has really good aims with the batarangs. Right? Superman, I mean, he might be able to throw them really hard, but maybe he doesn't really have great aim. Batman's not susceptible to kryptonite. Superman is. Batman's trained in martial arts. Superman can just knock the crap out of you. Batman's an earthling, right? And Superman is from Krypton. Okay. So do you get what I'm saying here? There's a whole lot of differences, but they're both members of the Justice League and they're both fighting for justice. They're both fighting for good, right? So while they have things that are different, they also have things that are similar. Fair enough? Yes? So let's think about exponents and logarithms as Batman and Superman. Can we do that for just a moment? Okay? The deal about exponents is you know about exponents. I can look at your test grades, and even some of you who got lower test grades, it was silly things that I could tell in your arithmetic that you messed up on, right? For the most part, you guys are pretty good at exponents, okay? That should bode well for you. Because if what I'm telling you about exponents and logarithms is that they're really closely related, they both fight for justice, right? Then that should have you feeling pretty positive if you understand exponents really well, right? Okay, so this little table right here has us guessing, and then has us using a table, and it has us graphing to see if we can find a value for x that works here. 2 to the x power equals 20. Well, we can do the guessing part relatively easy, right? 2 to what power equals something near 20? 2 to the 4th is 16, isn't it? Okay, so 2 to the 4th power is 16. What about 2 to the 5th power? What's 2 to the 5th power? Well, what's 16 times 2, guys? 32. Wouldn't 20 be in between those numbers? So wouldn't the value for x that I'm looking for be in between 4 and 5? Thank you. I just wrote down the wrong thing. Thank you for correcting me. Okay? It's in between 4 and 5, the value that I'm looking for. Okay? The value that I'm looking for is in between 4 and 5. Got it? Yes? Okay. So we could use a table and get closer, going to the 100th, and we can use our graphing calculator to graph both sides of the equation and find where they intersect, right? But do we want to have to do that every time, or do we want to be able to go straight to how we're going to solve this? Okay? So the problem is our variable is in our exponent. We have to have a way to undo exponents. For instance, we can undo addition, right? If we're adding 4, doesn't it look like n plus 4 equals a? But what if we're solving for n? What do we do with the 4? How do we undo it? Yeah, I subtract 4 here and subtract 4 here, so I get n equals a minus 4. Yes? And the way we undid it was to subtract 4. Or another way you could think of it would be adding the opposite, right? Okay. What if we're multiplying by 3? Doesn't that look like 3n equals a? Well, how do we undo that? How do we solve for n? Divide both sides by 3. So it looks like n equals a over 3. How did we undo multiplication? Divide by 3 or multiply by 1/3, right? The reciprocal. What's happening here in this box? 1/3. What's happening here in this box? Squaring. This is a square. Okay? How do we solve for n? So it looks like n equals the square root of a. So undoing a square would be a square root, right? Which brings us to this last one. What if it's 2 to the n power equals a? How do we undo that? Well, this is where I show you. This is where I tell you what we're going to do. And then I'm going to show you how to do it. Okay? This is what it looks like. Now notice how I wrote the 2. How did I write the 2? It's a subscript, right? In computer language, that's a subscript, isn't it? Okay. What's that called? How did we undo an exponent? A logarithm. Okay. Now some people say logarithm, like it's logarithm, and I mean I suppose that's fine. I mean, normal people say logarithm, like logarithm. Yes. So the way to undo exponents is to use logarithms. All right? Remember I told you a second ago that logarithms and exponents are very, very closely related? Now you're going to find out how. Because we're going to talk about the graph, what the graphs look like. Logarithms and exponents are, and then there's a blank. Well, let's use our context clues. That's another English type thing, right? That's what they tell you in English class. Look at the context clues if you're trying to find the definition of something. We're trying to fill in this blank right here. Looking at the context clues, I see that. Do you remember what that means? Absolutely. Exponential and logarithmic functions are inverses. How do you generate a logarithmic graph? How do you generate inverses? Switch x and y. So can we generate a logarithmic table if we have the exponential table? How? Whatever was x becomes y. Whatever was the y's becomes the x. Yep, we sure have done this before. That's why some people are comfortable with saying what they're saying. Okay, so if you kind of remember it, that's good. Okay? So now please take these, this table and plot it on the same graph as the exponential function already is. 0.25, negative 2, 0.5, negative 1, 1, 0, 2, 1, 4, 2, 8, 3. Did we just prove to ourselves that these are inverses of each other? How? Yep, it's reflected across the line y equals x. Okay, if I folded across that line, those two functions would be right on top of each other, wouldn't they? Okay. So we also have to know how to read logarithms. Do you know how to read that right there? Well, you need to. Okay? So first I'm going to teach you the definition. Does everybody have this graph? Okay? I'm going to teach you the definition. I'm going to teach you how to read it. Alright? You already know how to read this part, don't you? And this right here is an exponential form. It looks like an exponent though, doesn't it? B to the x power equals a, or b to the x equals a, or how else could I read it? Anybody have another way that they like to read these? No? I don't know any song about this. No, it's not, but that's okay. Okay? It's okay. B to the x power equals a is the way most people say this, right? This is exponential form. And this is logarithmic form. It means the same thing. It's written in different form. Okay? What is this letter? What is that called in exponential form? The B. What is that called? Or that's close. It's the base, right? Over here in the logarithmic form, guess what it's called? A base. What's this called? That's the exponent, right? Well, it's not called an exponent over here. It's called a solution, but we're going to go ahead and put exponent so we know where it goes. Is that fair enough? Okay. And what's the only thing left over here? The a. It goes right here. And it's called an argument. When they were first trying to decide what to call this, they could not agree, so they decided we'll call it an argument. I totally made that up. I have no idea why it's called an a. Why it's called an argument. Okay? It's just called an argument. That's just what they call it. Okay? So that's what we're going to call it. All right? But you need to know how to read this. Now, something interesting that happened to me a couple years ago. I was teaching with a young lady who had been teaching, I think, a year or two. And at that point, I think I'd been teaching like 10 or 12 years. That doesn't make me better. That just means I'd been teaching longer. That's the only thing. And some of my students came back to me after being in her class in pre-calculus and said, "You taught us wrong." So my first reaction as I think a decent teacher, I went to the teacher and I said, what did I do wrong? I got to fix it. If I did something wrong, I want to fix it, right? And she said, well, they're saying it differently than I say it. And I said, well, how do you say it? And she read it to me. She said, how do you say it? And I read it to her. And we realized the students just weren't understanding. We were saying the same things, but in a different order. But on an interesting note, neither one of us knew you could say it the other way. I was saying it how I was taught, and she was saying it how she was taught. So what we've done since is we teach it both ways. She and I both went to a different college. We were both taught by different professors, right? One professor taught it one way, one professor taught it another way. I don't know where you're going to school. I mean, I know for some of you, but I don't know where all of you are going to school. I don't know how they're going to teach it there. So I want you to have seen it both ways so that you aren't thrown for a loop or something. Fair enough? Okay. What I'm going to write on this line is how I say it, because at this point in time, that's what you're going to hear most often, right? Is me saying it. But I also want to make sure you know the other way. Fair enough? If I am reading this sentence right here, this mathematics sentence, I'm going to say log base B of A equals X. Okay? She said log of A base B equals X. She was taking care of the argument and then pulling in the base. And what I was taught was to read it left to right. Again, either one of them are correct. We even checked. We went and made sure that neither one of us were teaching it wrong. And sure enough, different professors teach it different ways. Okay? So just so you know, so you've seen it both ways, log base B of A equals X. That's how I was taught it. She was taught log of A base B equals X. Same thing. Okay? All right, one of the most important questions of the day. And I've actually already answered it for you. Let's see if you can figure it out or remember. Why do we use logarithms? What's the problem with this equation if I'm solving? Very good. Okay? So why do we use logarithms? To get the variable out of the exponent. Okay? Does that make sense? That's how we undo exponents, is by using logarithms. So the first thing I need you to do for me today is be able to go back and forth from exponential form to logarithmic form. Okay? Knowing that the base is a base, the exponent is our solution, and the argument is the other part. Okay? So 7 squared equals 49. What's that going to look like in logarithmic form? Log base 7 of 49 equals 2. Okay? The base is the base. The exponent is our solution, and then the argument is the answer. Okay? Now, earlier this crazy kid was like, okay, right, you wrote log in cursive. And I said, yes, I did. I wrote it in cursive right there. When I write the answer on B, C, D, and E, I'm going to write cursive, right? Not because I just think my writing's prettier than yours, so I'm going to make fun of you. Although, for some of you that's true, but we're not going to go there. Okay? If I wrote this, does that say 10G? Does that say 10G? 10 grams? Some of you are more familiar with that weight than others. What? I want it to be clear that I'm talking about a logarithm. I don't want it to be confusing if this is a 1 or an L, an O or a 0. Fair enough? Okay? If we were typing it, we'd make sure it was in italics. We're not typing, and we can't write in italics. Okay? That's not a challenge. Okay? So what about B? How are we going to write B in logarithmic form? Log base 3 of 243 equals 5. What about C? We're on C. Log base 6 of 1/36 equals, thank you. What about D? Okay. Log base 9 of 27. Very good. Now, guys, the only thing you're forgetting is the base. You're forgetting the word base. You can't just say log 4 because that's implying the log of 4. Log base 4. Log base 4 of x equals 9. Okay? What about F? Log base 2 of 20 equals x. What about G? Log base 8 of 32 equals x. Now, can you go back the other way? Okay. 2 to the x equals 64. Good. What about I? So x squared equals 64. Excellent. And what about the last one? 64 squared equals x. Okay. So then we have K, L, M, and N. What's wrong with them? There's no base, right? Okay, so let me ask you this real quick. If we're talking about root signs, what kind of root is that? And how do you know that even though there's not a little baby 2 right there? Because it's implied, right? Okay? What about this variable? What's the coefficient in front of it? But it's not written there. How do you know it's a 1? It's implied or understood, right? What's the exponent on that x? A 1. And how do you know that? It's understood, right? And it's implied. Okay? So when we have a logarithm with no base, that's going to be called the common log. It's the one they use most often. So it's implied, and it has a base of 10. I didn't stutter. It's 10. Okay? So now rewrite this from logarithmic into exponential form for me. 10 squared equals 100. Now, the good news about going from logarithmic to exponential when there's no variables, just like on this problem, is that it has to be right. Isn't 10 squared equal 100? Yeah. Can you think of any other combination of those three numbers that will give you a sentence, a math sentence that's true? Is 10 to the 100th power equal to 2? Is 100 to the 10th power equal to 2? Is 2 to the 10th power equal 100? No. Is 2 to the 100th power equal to 10? No, it doesn't matter. There's no other way I can put these numbers that will make a sentence that's true. So that's good news. Okay? Now, when there's variables like in L, we just kind of have to hope we did it right. Okay? But if we've done enough of these and we know the pattern, we should. Right? 10 to the negative third equals x. What about m? 10 to the fourth equals... Wait, does 10 to the fourth equal 10,000? Yes, it sure does. And what about n? 10 to the x equal 1/10. Okay, before we go on, I want you to look back at h, I, and j. Okay, these three right here. In this form right here, it made no sense. It meant nothing to you. But if I write it in exponential form, looking specifically at I right now, can you tell me what x equals? Because you've said to yourself, what times itself equals 64? Well, what times itself equals 64? 8. Is this something you could do fairly easy now that you wrote it in exponential form? Do you know 64 squared in your head? Neither do I, but we could plug it into our calculator fairly quickly. I haven't done this one. 64 squared would be 60 squared, which is 3,600, plus 4 squared, which is 16, plus 60 times 4. Time out. If you're going to make me do it, you're going to listen to me. 60 times 4, which is 240, times 2, which is 480. So 480 plus 16 is 496, plus 3,600, which is 4,296. Is that right? Oh, 4,096. I just didn't add right. So 4,096. Thank you. Guys, is h something you could figure out fairly quickly? 2 to what power equals 64? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. How many is that? How many fingers do you see? 6. X equals 6. Does that make sense? So sometimes when they're written in logarithmic form and you change them to exponential form, they're easier to solve, aren't they? This worksheet that I gave you called Rewrite the Log is telling you exactly that. It's in logarithmic form. It asks you to put it in exponential form and then solve it based on what you see in exponential form. Be quiet, please. No, I did all the ones on this page on purpose. Okay? So from logarithmic form, put it in exponential form and then figure out what x equals, just like we did right here. Okay? Please look at the third page that I gave you. And because I know that there's some of you that have already noticed this and are worried, please look at the bottom right hand corner. What does that mean? Page 3 of 4? I gave you page 3 and I gave you page 4. So what am I missing? 1 and 2, right? Why didn't I give you 1 and 2? They're dumb. They're dumb. I'm not giving you 1 and 2. They're dumb. They're saying, it's kind of like these up here. Here's 4 equations. Put them all in your calculator and see what they have in common and how they're different. Okay, that would be great if we have time. We do not. Plus, you already know this stuff because it's transformations. How many times have we done transformations this year? A lot. So tell me what you know. Here's the parent function. If a is greater than 1, how does this shift or change compared to its parent function? Say it. Vertical. Stretch. Absolutely. What if a is between 0 and 1? Say it. Vertical compression. What if a is less than 0? A is less than 0. It reflects over the x-axis, right? If it's a negative, that's what it's saying, if it's less than 0, right? Another way to say that? Okay. Now skip B for a second, because we haven't actually talked about that, but you'll see how easy that is in just a minute. What about H? What if we are subtracting H? So if it looks like H minus 2 or something like that, where is that moving? To the right. H is horizontal, right? Horizontal, so it's moving horizontally to the right. What about if we're adding H so it looks like H plus 2? Horizontal shift to the left. If you are going to write shift, make sure you remember your F's. It's important. Okay? What about K? What kind of shift is K? Vertical. So if we're subtracting K, that moves down. And if we're adding K, up. So all that's left that you don't know is B. And what's B in this problem? It's the base, right? This is the base. This is what you need to know about the base. It can also cause a vertical shift. Oh, that's not right. Don't write shift. Stretch, compression, or any guesses? Reflection. So here's what I will not do. I won't make you guess if it's A or B that's causing the stretch or reflection. Okay? I'll make sure one of them stays the same and the other one changes, so you know for sure if it's the A causing the reflection or stretch or compression, or if it's the B causing it. Fair enough? Okay? Look on the back of that page, please. Normally what we do to solve a logarithmic equation is I would put one side in y1 and one side in y2, find out where they cross, and that's the solution, right? Okay? But in a situation like this, how is this different? It's not an equation, is it? It's an inequality. Okay? What's always happening in an inequality? We always have to shade. Okay? So here's what the graph looks like when we put this in y1 and this in y2. Here's what the graph looks like. So obviously the horizontal line is the 2.5, right? So I want to know when this curvy part is less than or equal to 2.5. Well, doesn't it look like it's that part right there? So I have to figure out how to write that. Well, knowing what you know about exponents and now logarithms, is this going to cross the x-axis and go further this way? No, there's an asymptote, isn't there? Right there. Okay, so it's going to start at 0 and go to the right, but it's only going to go as far as the intersection, which they've found for you to be at 3.6. So it's going to be greater than 0, but less than or equal to 3.6. Now, they use the table here to find where these are like very close, very similar to get to the 3, to know that it's somewhere around 3. I would rather you guys find the intersection with analyze in your calculator. Okay? So also on this page, I need you to do 11, 12, and 13. So on this page, you're doing rewrite the log, all of them, A through L. And on this page, you're doing 11, 12, and 13. Any questions?